Question number 34. Which of the following best describe a substance in which temperature remains constant, while at the same time it experiencing an inward heat flow? It is not a condition when a substance face a phase change that is face a change in temperature. It's not a condition. So the temperature can be constant while it is there is a phase change. If you want to know more about it, you can read this chapter. So the answer is D. Question number 35. The energy here is in the form of kinetic energy. So let's us start with calculating the kinetic energy. The kinetic energy equals half mv squared. M here is half. Let's start calculating. M here is 0.003 times 240 to the power 2. All this equals 86.4 joule. But here we have the specific heat capacity in the unit of kilocalorie. So we have to convert it from joule to kilocalorie. How we can do this? By dividing it over 1186. Which equals 0.0206 kilocalorie. The kinetic energy will be equal the energy that's required to the phase change we don't have m, we want to know it. We have LF, which is 80, so it's 80 times m. You can solve this. M equals 2.6 times 10 to the power negative 4 kilogram. So the answer is D. Question number 36. Q1 here, which is the energy that's required to evaporate 0.5 gram of water, equals M here is 0.5 times LF, which is 540, equals 270 calories. This means the remaining water (149.5 gram). Q1, which is 270, equals Q2, which is the change in the heat or the internal energy of the 149.5 grams. M here in the mass 149.5. So that means delta T, or the change in temperature, equals, and is negative, here is negative, and here negative Q1 over MC. Q1 we just calculated 270 over the mass, which is 149.5 times specific heat capacity of water in the unit of in the unit of calorie, because we have Q1 in the unit of calorie. We have to be all the units will be the same, so it's the specific heat capacity in the unit of calorie of the water equals 1. So simply delta T equal negative 1.8 degrees Celsius. Question number 37. The ice here will face a phase change and the temperature change, while the T will face only a temperature change, not a phase change. So we will calculate ML for the ice because it faces a phase change plus MC delta T of the ice plus, or let me say, negative MC delta T of the T. Just we will substitute in the rule. The mass of the ice, we don't know it, so it's M times the latent LF of the ice, which is 3.33 times 10 to the power 5 plus the mass of the ice, which we also don't know, times the specific heat capacity of the ice, which is 4186, times the change in temperature. At, you start in 0 and end with 10, so the change in temperature is 10 equals negative the mass of the T, which is 1.8 kilogram, times the specific heat capacity of the T, which the T is a water, so the specific heat capacity of the T equals the specific heat capacity of the water, times the change in temperature in the T. The T starts with 80 degrees Celsius and ends with 10 degrees Celsius. You will solve for T and you will find that M equals approximately 1.4 kilogram. So the answer is C. Question number 38. The ice here will face a phase change and temperature change, and the water will face just temperature change, and the aluminium will face just a temperature change. The water will still water, and the aluminium will still aluminium in the solid state, as it is a container, and the ice will be converted to water. So you will calculate ML for the ice plus MC delta T of the ice. I can't write a specific symbol for every material because I don't have the ability to do this in my keyboard, but please concentrate about what I say. Plus MC delta T of the water plus MC delta T of the aluminium or the container. All of this will be equal to 0. We just will substitute in the rule. LF of the ice is 3.33 times 10 to the power 5 times the mass of the ice. The mass of the ice here is 500, 1500 over 1000 to convert it to kilogram. As LF here in the unit joule per kilogram, and the specific heat capacity of the water in the unit joule per kilogram. So we have to convert it from gram to kilogram. Plus the mass of the ice again, which is 50 over 1000 times the specific heat capacity of the ice, which is 4186, times the change in temperature of the ice, which is T minus 0. We can not write 0, plus the mass of the water, I'm sorry, which is 200 over 1000 to convert it to kilogram, times the specific heat capacity of the T. Actually, the specific heat capacity of the T equals the specific heat capacity of the ice equals the specific heat capacity of the water, because they all water. 4186 times the change in temperature, which is T final for the whole system, minus the initial temperature of the water, which is 30, plus the mass of the container, which is 80 grams over 1000, times the specific heat capacity of the aluminum, which is 900, times the change in temperature, which is T minus 30. Okay, it is a little bit big. You have to solve for m. All of this equals 0. After solving this big equation manually or by using calculator, I don't think that the calculator can solve it, so you have to solve it manually. So the answer will be approximately 9.5 degrees Celsius. Question number 39. The ice here, or the dry ice here, will face just a phase change. It will not face a temperature change, and the water here will just stay water. There is no change in the phase of the water, just will face a temperature change. So here we have Lm of the ice equals negative mc delta T of the water. Let us substitute. The mass of the ice is 125 gram times the heat of vaporization equals negative m, the mass of the water, which is 500, times specific heat capacity of the water, times the change in temperature, which is 29 minus 66. You will solve this manually or by using the calculator, and you will find that L simply equals 148 calorie per gram. So the answer is D.